Hello everyone and welcome to another video. So today we are on to week 9 of our flight mechanics class. So let's go and take a look at the roadmap of where we're going this week. Again, this is very exciting because as you saw, weeks 1 through 8 was spent doing a lot of background work in terms of developing the equations of motion, the core flight mechanics analysis in order to get an aircraft model. And then last week we finally were able to linearize that nonlinear system about some trim point, and now we've got a linear model in our hands. So that's what we want to start dealing with now in week 9, is now that we finally have a linear model of our aircraft, what are we going to do with it? So the first thing we're going to do is we are going to perform what's known as a similarity transformation. So to do that, I want to have a very abstract, sterile mathematical discussion on what is the idea of a similarity transformation, as well as how this relates to matrix diagonalization. So that's what this first video here is. This is a pure linear algebra discussion. It has nothing to do with dynamics. It has nothing to do with aircraft. It's just what is similarity transformations for matrices and how does that relate to a general sterile mathematical concept. Then, once we have that idea down, we're going to apply the math to an actual dynamic system. So that's what this next video is if you now have a dynamic system, like our linear aircraft model, how would you perform a similarity transformation on the system, and what does that actually do? So these first two videos, it's about an hour and a half long discussion on the concept of similarity transformations and how they apply to dynamic systems. Now, we should also have a corollary side discussion. Now that we have a linear system, let's talk about what are the eigenvalues of your linear system and what do they mean. And also, what's almost more interesting is not just the eigenvalues, but there's this idea of modes of linear systems. And we're going to see this is effectively a core behavior of how a linear system is going to behave. So we want to have a little bit of a discussion here in this third video, talking about what is the idea of eigenvalues and modes of a generic arbitrary linear system. Okay? Once we have that, what we should probably also talk about is, remember, week 9 is you have a linear system, a linear model in your lap, right? And you're able to play with this linear model. But we know this linear model, in this particular case for our flight mechanics class, right? This came from our nonlinear dynamic model that we developed way back here in week 6. So we have a nonlinear model. We went through this process of finding a trim point, numerically linearizing the system, and obtaining a linear model. So now we sort of have these two models, right? We have the nonlinear model, which is this high fidelity, 6 degree of freedom, nonlinear dynamic aircraft model. And now we've got a simplified linear model. So we've got two models in our hands right now. And what this video is talking about is well, these two models are similar but not exactly the same thing. And if we want to apply an initial condition in one case, how do we apply a similar initial condition in the other system? And similarly, what about the inputs? Well, if you have an inputs going into the nonlinear model, how do you have those equivalent inputs going into the linear system? So what this video talks about is how to translate inputs, outputs, and initial conditions between a linear and a nonlinear dynamic system. So, with that being said, now at this point we have a good methodology to go ahead and analyze our linear model and then look at results and apply them not just to the linear model but also translate them and apply them back to the nonlinear system to see if we have similar behavior. Okay? So the last video then, with that in mind, the last video for this week is, well, let's look at our particular aircraft, right? All of this discussion, these first 4 videos, are fairly generic in the sense that it's just math and it's just talking about generic generic dynamic systems. Well, now, how do we take all of these ideas and apply it to our specific aircraft? So we're going to see that this is really a lot of fun because this is where the engineering theory meets with the actual practical application. So for those of you who are pilots out there, I'm sure you've heard of people talking about, oh yeah, this aircraft has a certain fugoid mode or a short period mode or a Dutch roll mode. They talk about how aircraft have these general behaviors, and pilots will often talk about them and try to describe them in sort of these fuzzy feeling ways, right? Well, now as an engineer, we can actually talk about exactly what's the math behind it. How do those ideas translate to these mathematical constructs and concepts, namely things like eigenvalues and modes of linear systems. So this last video is really tying all of this together and looking at our specific aircraft and trying to marry the ideas of these mathematical concepts with an actual practical description of how an aircraft behaves. So this should be a lot of fun. This really is the culmination of, 9 weeks of discussion to get to this. We've put all of the engineering, all of the math in place so that we can really get down to this, and this is really where it gets, hopefully I think it ties a lot of these ideas together. So with that being said, let's take a look at the homework. So homework 9 is over here on the side of the screen. And again, yay, this is actually the last homework for the class. So even though there's 10 weeks of class, we will not be having homework 10 because we're going to dedicate that time and let people work on their final project. So instead, what we've got, again, last set of homework, let's take a look at this. So problem 1 is, again, let's take a look at the linear model that you obtained last week, right? Homework 8, you were basically obtaining a linear model of an aircraft flying straight and level at 85 meters per second. Now, you can take that linear model, and now all I'm asking people to do is perform a similarity transformation, and this similarity transformation is really simple. All we're going to do is we are going to reorder the states. So I'm going to want to stack the longitudinal states, these things that I'm calling x long, on top of these 4 lateral directional states, which we're calling x lat. So you see that this new state vector z, it's nothing more than the original state vector, but it's just reordered in some fashion, okay? And what's interesting is when you do that, hopefully something is going to happen. You're going to see the matrix is going to be reformatted in an interesting fashion, which is going to allow you to answer part B. What I'm going to claim is that at this particular operating point, the linear model that you have is decoupled. And what that means is, again, without giving too much away, is when you perform this transformation, the similarity transformation on your linear system, something very interesting is going to happen with the structure of the A matrix. So I'd like you to examine that and see if you can make a case, a mathematical discussion of why we sometimes say that these modes, the longitudinal and the lateral directional states, are decoupled in this condition. So that's what problem 1 is applying this to your old system. Okay, let's take a look at problem 2 now. So problem 2 is, again, let's consider now, in problem 1, you have a full 9-state linear system, okay? By the end of this, if you answer that yes, you're able to decouple the system, what we're going to be able to do is you're going to take that single 9-state system and be able to break them up into several different smaller linear systems. One of these linear systems is what we're going to call the linear longitudinal model. And again, when you watch these videos, hopefully this is going to make a lot of sense what I'm talking about here, but you're going to see that this is basically a smaller 4-state linear system. So for parts A through C, I only want to look at the 4-state linear longitudinal model, okay? And all I'm asking you to do here is go ahead and look at the eigenvalues and eigenvectors of this longitudinal A matrix and make some observations based on what those are. Okay, what that's going to allow you to do is also choose an appropriate set of initial conditions that are going to allow you to excite certain modes of the system. Okay, so you can do that now with your linear system in part B, and then in part C, I just want you to take that same initial condition that you use to excite these modes in the linear system and try to translate those initial conditions so that you can excite those same modes over in the nonlinear model. All right, and again, that's the whole point of this video over here is, well, how do you translate these initial conditions from one model to the other? Okay, and then for parts D, E, and F, we're going to do the exact same thing, but now we're going to consider the lateral directional linear model only. Okay, and again, it's just a rinse and repeat, so nothing too much to chat about there. Okay, let's move on now down here to the last problem, problem number 3. Okay, problem 3 is interesting. Before we dive into it, let's step back and look at the roadmap of where we are. So remember, we started, week 1, we didn't know anything about flight mechanics. We started from basic, simple vector mechanics. We developed equations of motions. We looked at rotating reference frames. We talked about Euler angles. We did all of this stuff to basically get a nonlinear dynamic system, right? And then we did more work, right? We put some tooling in place so we could trim this nonlinear aircraft model and then linearize the nonlinear aircraft model, and finally analyze effectively the behavior and the stability of this system, right, by looking at the linear system. So over 9 weeks, we've developed a lot of tools, a lot of code, a lot of procedures that allow us to have this entire workflow of basically develop a dynamic set of equations, trim those, linearize those, and analyze it, right? That's the workflow that we did in these 9 weeks, okay? So all we're doing here in problem 3 is we're effectively looking at doing that process, but doing it for a bunch of different conditions, because this is where it gets really interesting. So let's just talk this through. So a lot of times, right, I'm sure you've heard in your introductory flight mechanics class that a lot of times people will say the back of the envelope discussion is, they'll say, you know, the rule of thumb is that the longitudinal stability of your aircraft, it depends a lot on where the center of gravity of your aircraft is located, right? If it's in front of the neutral point, you are usually longitudinally stable. If it's behind the neutral point, it's unstable, right? And that's what people just kind of say. And they don't back that up with a lot of equations or analysis, right? So what this problem is about is, let's do the analysis to see, when we have this rule of thumb here, where does this come from? How does this show up in the actual dynamic equations, right? Okay, so to do that, the first part is, again, a little bit of a rule of thumb. What we're doing here is we're kind of almost conducting like a virtual wind tunnel test, right? So a lot of times people will ask you to plot the pitching moment about the center of gravity as a function of alpha, right? And usually this is expressed in the wind axis if you're talking about this from a wind tunnel discussion. But long story short, you have this plot of pitching moment versus alpha, right? And again, what a lot of people say is that, okay, if the slope of this curve is negative, you're stable. If the slope is 0, you're neutrally stable. If the slope is positive, you're unstable in the longitudinal direction again. So all I want to do in part A is just, let's make these plots, okay? All you're going to do is go ahead and virtually change the center of gravity of your RCAM aircraft. So remember, the RCAM aircraft that we developed back here in week 6, right, is there was some parameter in there that was setting the center of gravity. In fact, I think it's called XCG, right? And I can't remember exactly where it's nominally located, but what I'd like you to do is, you've got code now, and you can easily, with one line, just change the location of the center of gravity, right? Move it front, move it back, move it all over to a couple of different locations throughout this range, between minus 0.3 C bar to 0.5 C bar, right? And all you're going to do is go ahead, move the center of gravity, and then perform a virtual wind tunnel run where all you're going to do is go ahead and change the angle of attack of the aircraft, right? That this aircraft is experiencing, and then have your RCAM model output what is the pitching moment about the center of gravity expressed in the wind axis. So you're going to have to modify your RCAM function ever so slightly, right? So that it has one more output, right? And allows you to also change the position of the center of gravity, right? So all this is doing is basically you take homework 6, where we built our RCAM aircraft, make a small little tweak to it so that you can change the CG, and also you can now input different U and W values to change the angle of attack, right? Okay, so what this is going to allow you to do is basically conduct a virtual wind tunnel test using your RCAM aircraft, right? And what you can then do is you can run this sweep, right, this alpha sweep, just change your angle of attack through a whole bunch of different values, right? And then go ahead and set one CG location and then do this sweep. And then change the CG location and do another sweep. Change the CG location, do another sweep, etc., right? And I feel like this is probably one of these situations where it might help to just look at a picture rather than hear me discussing this. So I'm expecting something like this, right? So what you're doing here is, you can see this is my results where I went ahead and, you know, this red line is the line that I got when I swept alpha from -5 to 15 degrees with a CG location here of 0.5 C bar, right? And then all I do is I move the center of gravity back a little bit to 0.4 C bar, right? And I get this next line, and etc., right? So you can do all this, and you can generate all this from the comfort of your own home, right? You don't have to go to a wind tunnel to do this. You can go ahead and just do this right here, okay? And then, based on this plot you've got over here, can you estimate where the neutral point of this aircraft is, where you become longitudinally neutrally stable, okay? All right, now, a lot of that is sort of, I don't want to call it hand wavy, but it's not actual full analysis, right? That's what I'd like to do now in these last parts. So for part C, let's go ahead and actually analyze this aircraft in some configuration and see is it stable or not for a given CG location. So what I'd like you to do is basically rerun your trim code. So remember, in week 7, you wrote yourself some trim code that allows you to trim the vehicle at steady state, straight and level flight at 85 meters per second, right? Basically at cruise. Well, go ahead and just modify that code so now you've got the aircraft in a descent at glide slope of -3 degrees and slightly slower at 67.6 meters per second, right? And what you can do is you can run that trim code for a given CG location. So for each one of these plots that you made in the previous section, right, you're going to trim the vehicle at that condition and at this CG location. So this red one, right, is 0.5, etc., etc., etc. Right? So you're going to have, in this case, as many trim points as you have curves. Okay? And then what you can do is we also now have linearization code, right? That's what you did last week in week 8. You now have a system to go ahead and numerically linearize your aircraft about any given trim point. So take each one of those trim points and linearize your system about each one of them. So this is going to give you now, for each one of these curves, you now have a different trim point and also a different linear model, right? And now that you have all these different linear models, we're now in a good position to actually talk about stability from a mathematically and engineeringly rigorous platform. So for part E is, well, stability cares a lot about the eigenvalues of these linear models. So just go ahead and look at these eigenvalues, and hopefully what you should see is that for configurations like this red curve, right, the eigenvalues are all in the left half plane, meaning you have a stable linear system. But as you start moving this CG backwards, something is going to happen with the eigenvalues, and I don't want to give this all away. I want people to have a little bit of a chance to explore this themselves, but you should see the eigenvalues move as you change the CG location, right? And again, that makes perfectly good sense, right? You are physically changing the system by changing the center of gravity of the aircraft. Therefore, I would expect the linear models to change, and therefore I would expect the eigenvalues to change, right? So that's what we're doing here at part E, is you're trying to assess where do you have a problem, right? One of these values of these CG locations should probably yield some type of problem where the aircraft is going to become unstable. So the last thing we're going to look at here is, okay, if it's unstable, why don't I go ahead and just simulate that, right? I'll simulate the linear system and I'll simulate the nonlinear system to verify if the system is stable or not. So yeah, problem 3 is really a culmination. You are doing a ton in this problem, so I would obviously recommend don't procrastinate. And also, this is a lot of fun because if you think about this, this is tying together 9 weeks of our discussion, and we're basically doing a full sweep of different parameters and looking at sensitivities, and we're able to do this using all of these tools that we've developed. So this is a lot of fun, and I hope you're as excited as I am about this type of analysis. So let me see. I think with that being said, that is a good spot to leave it for week 9. We're almost there. So we've got one more week left, and next week we will talk about some fun things that we can now do with our RCAM system. So really, at the end of week 9, we're kind of getting to the end of the engineering analysis. So we're just going to look at some bells and whistles next week. So email me if you have any questions. Let me know how things are going. And otherwise, I think I'll sign off, and I'll look forward to seeing everyone next week. All right, talk to you later. Bye.